if you're watching this, you missed day 1 of our week 9 Foundations of Tech class. We're talking about bridges. I hope you guys are doing well. Let's get started. So by the end of today, you should be able to identify different types of bridges. That's not as important to me as you understanding how the forces within a bridge act. So how are the forces mitigated or taken advantage of through bridge design? And how can you use those ideas in other buildings? That's what's really important. You should also be able to compile and research information about a historic bridge, which is going to be your assignment. But more on that later. First of all, we talked about the spring break, so hopefully yours went well. I spent mine relaxing. If you didn't get a chance to tell me, I do appreciate hearing about your lives, so let me know. How did it go? Now, types of bridges. We're going to be talking about these 7 as the main ones. So we got arch, beam, cable stayed, suspension, truss, cantilever, and movable. And as we'll see later, sometimes you can have bridges that are kind of hybrids of a couple of these. So it's not necessarily just one. It's several of these ideas smushed together into one bridge. So let's go ahead and see what these are all about. Now, please remember, all bridges work because of compression and tension. Every member inside that bridge that's structural is going to be under either compression or tension, or maybe both, depending on which side of that particular member you look at. And how that member then distributes or absorbs that pressure determines how sturdy your bridge is going to end up being. So arch bridges are one of the most ancient and kind of straightforward ways to tackle this issue. Essentially, you build up a structure where the force is distributed to either side. This is a really, really old bridge called the Stari Most in Bosnia. I'm not sure if it means the same thing in Bosnian, but in Russian this would mean old bridge. Very stunning. You can really see how thin this design can get at the top. Here's a bridge of Alta across, of course, the Arakfos River in Alta. Here's one in Turkey, the Kuyumbaba Bridge. So all of these bridges have the same idea. Some of these are just one arch, some of these are many arches next to each other, but they distribute the force the same. So in this case, we have a lot of compression going on here. So these are compressive forces going on the top of our bridge, and they're being dissipated out to the sides. Now, there's a really cool video right here that I highly recommend you guys watch about how chains are kind of like the opposite, but work the same way as arches. Now, chains, instead of these compressive forces, have to deal with tensile forces as they're being pulled down by their weight, but it turns out a successful arch is one that can pass what's called the chain test. That is to say, if you were to take a chain and hang it freely, if the chain can go inside the profile of your arch, then that arch is a viable one and it will stand up under its weight. Whereas if the chain cannot fit, that means that arch is no good. It's not going to work. So that's really, really interesting, and we're going to see that same idea later on in a different kind of bridge. So I highly recommend you watch this video. Now, the next kind of bridge we'll talk about is the beam bridge. This is the simplest, most straightforward solution you can possibly have. It's literally just a straight thing across whatever you're trying to span. Here's a really, really long beam bridge. This is this is in Louisiana, rather, across Lake Pontchartrain. If I'm pronouncing that wrong, please somebody correct me. And the problem with these kinds of bridges is, yeah, they're straightforward, but you're not really taking advantage of these more interesting geometrical approaches to bridge building. So this works quite well if you use a really, really powerful material like concrete, but you are not really dealing with these forces well in this particular instance. Cable-stayed bridges have a bunch of these pylons with cables, and the cables allow you to dissipate some of the force. Here's one in Japan. Pretty cool. So you have a cable stay and a pylon. The pylon is being pressed down into the ground. It's experiencing compression. And then there's a lot of tension over here on these cable stays that's essentially taking out the pressure from the actual surface of the bridge. So the surface of the bridge is not under as much tension or compression as a result. So that's pretty nifty. Now, suspension bridges have a similar thought process to them, but they actually are slightly different in their approach. So what we've got is this upside down U shape. So you should be thinking to yourself, arch perhaps, but it's almost like the opposite of an arch. So the way these work is kind of like the chain as the mirror image of an arch. You've got your quote-unquote chain up here connected by these trusses to the actual bridge itself. As the trusses are pulled apart, they are under tension. They create tension in the actual arch itself, which of course is the opposite of the compression you would see in an arch. And that tension then translates to compression in the pylons on either side. Now, as with an arch, it's very, very important, if you have an arch, to make sure the sides of it cannot slide out, as that would ruin the arch, right? Similarly, in a suspension bridge like this, the ends of it are actually being pushed outwards. So it's very, very important that the bridge cannot push its way out and just collapse under its weight. Truss bridges use triangles. Triangles are the strongest shape. Arches are pretty good, but triangles are king because you can always add more triangles. There's no chain test with triangles. You can just always pile in more, and the more you have, the stronger it becomes. This is a type of design called a Bailey bridge, which was very popular during World War II. As you can see, all these triangles really work together to hold it up. This is a famous bridge across the Hudson River that uses this idea underneath. Very nice and aesthetically pleasing. And as you can see, these triangles deal with both compression and tension very well by distributing it evenly throughout the structure. So essentially some of these forces end up canceling each other out, which is quite great because you don't have to have the materials withstand as much force that way. Cantilever bridges we're not going to talk about much, but essentially the bridge is fixed on one side and not the other. And then movable bridges can be all kinds, but as you can see, this one here is a suspension bridge, but it can rise up and down. It's a drawbridge. This is a really famous bridge called the Tower of London. So guess the bridge. You guessed suspension. You're correct. You could have also guessed truss, as these little members here could be said to be a truss, or beam would be pretty close. How about this one? This one's an arch bridge. It's got lots of stuff on top of it, but really the bridge itself is just an arch. This guy here, what do you think? So this one's interesting. This one's a beam bridge, but it's definitely got truss elements on either side that are supporting it, so it could be said to be a truss bridge. And also these guys here on the sides are cable stays. Now normally you want those down the middle as it would be more effective there. But certainly this still counts as a cable stay element. So this is combining cable stay, truss, and beam bridge all together. So there you go. That was our lecture on types of bridges. Now to actually complete your assignment, you're going to need to go to MyMCPS, log in, click on Modules, and complete assignment 12. You need to file a short research essay on a bridge that you like. I leave it up to you. The bridge must be still standing. I recommend historic bridges as they're more interesting to write about usually, but it's your choice. You need to include who designed it, what type of bridge design is it, out of the ones we just listed. When was it designed? How long did it take to build? If you can't find this information, that's okay, but please make sure you include that you tried to locate it and it just wasn't out there. Where and what river? And why was it made? This is really important. You don't just put bridges willy-nilly wherever you like. There was some strategic importance to putting it where it is now. Was there a social need, an industrial need, an economic need? What made people want to create that bridge? How much did it cost? And then what problems did it solve? Again, I know that it lets you go from point A to point B, but why did people really want to do that at that particular location, at that particular time? What is the motivation? Without understanding motivation, we can't really understand technology. And last but not least, no technology is foolproof. There's always some kind of problem. So what problems did this bridge cause? Was it an environmental problem, perhaps? Was it a problem during construction that somebody encountered? Was it a problem of negligence, misuse? What was the issue with this particular bridge? And no bridge is perfect, so there's always something to write about there as well. Please make sure you cite your sources, don't plagiarize, and if you have any questions, please let me know. I'd be happy to help. Have a good day.